Problem number 1 asks us to find the horizontal distance that the water travels as it first begins to drain from the tank. And so to start this problem, I kind of labeled a couple different terms in this diagram. So we've got our y1, which is the height of the water in the tank. We've got y2, which is the height of the spout in the tank. And then I defined delta H as the difference between that y1 and y2. And so we're trying to find that distance x that the water travels horizontally as it exits the tank. And whenever we're looking at a fluids problem and we're examining something at two different points, we know we're going to be using Bernoulli's equation. And it's really important that you're picking the correct points before you start. And so in this one, I set my first point to be on the surface of the water at the top of the tank. And that is almost always going to be one of your points in an equation like this. And it's great because your pressure is at 1 atm there, you're exposed to the atmosphere. And also, a lot of times in these problems, the area is so large at the top of the tank and the water would be moving so slowly as it drains from the tank that a lot of times you can assume that your velocity at that point is 0. And then for my second point, I chose it to be right at the exit of the spout. And the reason I chose that point is because, again, it is exposed to the atmosphere, so I'll be able to cancel out those pressures because it's at 1 atm. And the exit velocity, that V2 at that point, is going to be a variable that we're looking for in order to use some kinematics to be able to solve for that x. To start, let's rearrange Bernoulli's equation to isolate for that V2, because that's the velocity that we're going to be looking for in order to find that distance x. So rearranging the equation, we get that V2 squared is equal to V1 squared plus 2 over our density multiplied by our pressure 1 minus pressure 2 plus 2 times our gravity multiplied by our difference in heights. And I skipped a couple steps there in my rearranging, but if you want to pause the video and see how I did that, I'm sure you could figure that out. And now that we have this equation, we can cancel a couple things out. As I mentioned earlier, our pressures are both of our points are exposed to the atmosphere. So we can go ahead and cancel out that pressure term because those are equal. And then we can go ahead and substitute this y1 minus y2 in for our delta H. And so rewriting this equation, we're left with V2 squared is equal to V1 squared plus 2 times our G times our delta H. And as I mentioned earlier, our velocity at point 2 is going to be much greater than our velocity at point 1. And it's actually going to be so much greater that the velocity at point 1 is almost going to be negligible in this equation. And so we can go ahead and cancel that term out, just set it to 0, and be left with V2 squared is equal to 2G delta H. But if you don't trust me that can be canceled out, we can go and look at our mass flow rate equation, which is our density times our area times velocity, and those will all be at point 1, is equal to density, area, velocity at point 2. And so if we look at the areas, the area at point 1 is this large area where the water's draining from. And so that's a pretty big area. And then we've got a small little area at the exit of the spout, which is our area 2. And so because our area 1 is so much greater than our area 2, and our densities are equal because it's water, so we cancel those out, we can assume that our velocity 2 is significantly greater than our velocity 1. And that's why we're able to cancel out velocity 1 in this equation. So to solve for our velocity at point 2, we can just move that square over, and we're left with velocity 2 is equal to the square root of 2g delta h. Now that we have our velocity at point 2, we need to think about how we can convert a velocity into a distance. And so that brings us back to kinematics. If we remember the kinematics equation, x is equal to VIT plus 1/2 AT squared, we can use that equation in order to convert our velocity into a distance. But to do so, we're going to need a time, right? Because we're looking for that delta x, and we have our velocity. We know that there's no acceleration in the x direction, but we don't have a time here, so we're missing time. And so to solve for time, we can use our y direction and then use that time to then solve for that x distance. So using our y direction first, we know that there's no initial velocity in the y direction at point 2. The water's coming out horizontally. And so we can go ahead and cancel out that initial velocity term. Our x here, we know it's y2, and because that's the distance that the water is going to travel from the spout to the ground. And so we can rewrite this equation as y2 is equal to 1/2, and we know our acceleration is gravity times t squared. And then rearranging that, we can solve for our time, and we're left with our time is equal to 2 times y2 over g, all under square root. Next, we can use that along with our calculated velocity at point 2 and plug that back into our kinematics equation to solve for that distance x that the water travels. And so we get x is equal to our initial velocity, which is at v2, times t, and then there's no acceleration in the x direction. The only acceleration on the water at that point is due to gravity, and we're going to not consider the effects of air resistance in this problem. And so if we plug in what we've got, we're left with x is equal to our term for v2, which is 2 times g times our delta h, multiplied our term for time, which is the square root of 2y2 over g. Finally, we can go ahead and combine those terms and get a solution for this problem, and we're left with x is equal to the square root of 4y2 delta h. And so this problem is a little tricky because you're not given any numbers. You've got to label a lot of things for yourself. However, if you walk through Bernoulli's equation and use some kinematics and make sure you get those points in the correct spots and you're able to cancel out the pressures, you can solve this one. So I hope that helped.